Welcome to the Explainer. We often think of artificial intelligence as this completely abstract thing, right? Just software, algorithms, and data floating invisibly up in the cloud. But here's the reality. This hyper-advanced, invisible software is slamming headfirst into a very physical, multi-billion-dollar manufacturing bottleneck. It literally all comes down to three things: metal, water, and heat.
Okay, let's dive into this by looking at two vastly different realities. Back in 2017, a standard AI graphics processing unit, or GPU, consumed about 300 watts of power. You could basically just blow air over it with a simple fan to keep it cool. But fast forward to the projected chips of 2028, and we're staring down 3,000 watts or more per chip. That's a tenfold increase. To put it in perspective, trying to cool these new chips with air is kind of like trying to put out a roaring campfire with a hand fan. The core problem isolating the entire AI industry right now is massive, absolutely unmanageable heat.
And to solve that heat problem, the industry requires exactly 15,900. That's the estimated number of new, highly specialized CNC machining centers that literally must be built and deployed worldwide by the year 2030, just to manufacture liquid cooling parts. So the hero of the AI revolution? It's shifting right before our eyes. It's no longer just the software engineers out in Silicon Valley. It's rapidly becoming high-precision CNC machinists and manufacturing hubs across Asia.
Here is our agenda for today's Explainer. First, the AI heat problem. Second, the liquid cooling solution. Third, the hidden CNC boom. And finally, Asia's supply chain shift.
Section 1. The AI heat problem.
To understand the physical limits of our current hardware, we've got to look at what the industry calls TDP runaway. That's thermal design power runaway. If we walk through the timeline of NVIDIA GPUs, the progression is just staggering. We went from the V100 back in 2017 at 300 watts, right up to the H100 in 2022 at 700 watts. And honestly, 700 watts was essentially the absolute physical limit for traditional air cooling. Now, with the 2024 Blackwell generation hitting 1200 watts and the upcoming 2026 Vera Rubin architecture estimated at 1800 watts, well, the transition from air cooling to liquid cooling is completely irreversible. You simply cannot operate these chips without pumping liquid directly to them. No way around it.
But hey, make no mistake, this is absolutely not just an NVIDIA problem. Every single major player is hitting this exact same thermal wall. AMD's upcoming MI355X, Google's TPU V7, Amazon's Trainium 3, and Microsoft's Maya 200 chips, they are all standardizing liquid cooling. The entire global computing infrastructure is literally changing its plumbing just to survive the heat.
Section 2. The liquid cooling solution.
So, how exactly are the tech giants responding to this massive thermal wall? Well, they're throwing capital at it. $775 billion of capital, to be exact. That staggering number is the estimated combined 2026 capital expenditure of the big five hyperscalers.
Now, what's really interesting about this breakdown is the sheer concentration of wealth being deployed to solve this infrastructure bottleneck. We've got Amazon at $200 billion, Microsoft and Alphabet at $190 billion each, Meta at $145 billion, and Oracle pushing over $50 billion. The absolutely crucial takeaway here? An estimated 75% of this capital is going directly toward AI infrastructure. Sure, they're buying the chips, but more importantly, they are buying the massive physical systems required to keep those chips from literally melting. At the very heart of these billion-dollar systems is a relatively simple-sounding object: the cold plate. This is the hero component of what we call single-phase direct-to-chip cooling. Basically, it's a precisely machined block of metal, usually copper or stainless steel, that's mounted directly onto the silicon itself. Inside this plate are incredibly tiny microchannels. Coolant flows through these channels, absorbs the massive heat directly from the chip, and safely carries it away. But here's the catch. You can't just go buy a cold plate off the shelf. Building liquid-cooled servers requires a really strict four-tier supply chain. First, the chip maker, like NVIDIA, designs the silicon. Second, massive assemblers like Foxconn build the actual servers. Third, specialized module suppliers like AVC or Delta design the cooling loops. But it's the fourth tier, the CNC machining part supplier, that physically carves those cold plates and manifolds out of solid metal. And this is exactly where the hidden manufacturing value lies.
Section 3. The hidden CNC boom.
These new cooling modules require massive, and I mean massive, amounts of high-precision metal processing. If we map out the annual global demand for the CNC machines specifically needed to carve these liquid cooling parts, The growth curve is just explosive. Look at 2024, only about 200 new machines were needed. But by 2026, as the new generation of chips rolls out, that jumps to 1,300. By 2030, we're looking at 4,900 new machines needed in a single year. That's roughly a 25x scale-up in annual demand in just over 5 years. It's wild.
So why do we need so many machines? Well, it all comes down to one specific metric: 75 minutes. That is the exact manufacturing cycle time required to CNC machine a single stainless steel top cover for just one of these cold plates. We're not talking about cheap, fast plastic molding here. This requires intense, high-speed 16,000 RPM spindles grinding through incredibly tough metal to create flawless water channels. Because think about it, if a single droplet of water leaks inside a 100-kilowatt server rack, the whole system fails.
And this brilliantly illustrates the divide in the manufacturing requirements. While small connecting fittings might take, 5 to 10 minutes on a standard machine, the critical large top covers and manifolds take well over an hour. Plus, they demand expensive, high-speed machines with specialized through-spindle cooling. This hardware demands highly specialized, time-intensive manufacturing. Basically, you need thousands of machines running 24/7 just to keep up with the tech giants' orders.
Because of these intense processing times, the median annual revenue capacity per CNC machine in this sector converges at roughly $700,000. So, when you multiply that $700,000 by the 15,900 machines needed by 2030, well, you validate a massive multi-billion-dollar secondary market for manufacturing equipment that is entirely dependent on AI's growth.
Section 4. Asia's supply chain shift.
So where is all this metal actually being cut? When we analyze the regional demand for these new CNC machines, a highly concentrated structure emerges. China commands 32% of the demand, mostly driven by domestic self-reliance initiatives. The ASEAN region follows closely at 28%, and Taiwan sits at 13%. The US only accounts for about 12%. What you really should take away from this is that Asia accounts for a whopping 73% of total global demand for AI liquid cooling manufacturing.
But the most dynamic shift is happening right now in Southeast Asia. Research estimates that 50% of Taiwan's electronics manufacturing service capacity, those are the giants who actually assemble the servers, is shifting into the ASEAN region by 2026. This is a massive geographical pivot. It's driven by a mix of geopolitical risk management and just the sheer need to build localized supply chains for these incredibly heavy liquid-cooled racks.
This supply chain pivot has essentially created a 4-pillar hub structure in Southeast Asia. Thailand is becoming a massive base for cold plate production, serving giants like Google. Vietnam is scaling rapidly with Foxconn and other module makers. Malaysia is quickly becoming the assembly and data center hub, boasting a crazy 6-gigawatt data center pipeline. And the Philippines is carving out a really specific niche in high-precision top-cover manufacturing. Every single country is playing a distinct, specialized role in keeping AI cool.
All right, let's summarize our core takeaways from this explainer. First, the shift to liquid cooling is completely irreversible due to the extreme heat these chips generate. Second, this creates a $45 billion market for CNC machined parts by 2030. Third, to hit that target, the world needs nearly 16,000 new CNC machines. And finally, the ASEAN region is rapidly cementing itself as the new global manufacturing hub for this absolutely critical infrastructure.
But as we wrap up this explainer, I want to leave you with one final provocative thought. We've just spent this time mapping out the incredible effort required to cool these chips. However, major memory suppliers like Samsung and SK Hynix have recently warned of severe high-bandwidth memory shortages stretching well into 2027. So it really begs the question, even if we build all the cold plates in the world, are memory constraints the real ceiling for the AI revolution? It's a sobering reminder of just how fragile and deeply interdependent the entire AI hardware ecosystem truly is. Thanks for joining me on this deep dive, and keep learning.